Okay, Mr. Repka, and I like to do these videos because it gives you a chance to watch these videos anytime that you need to, whether you need to watch it again at home, pause it, watch it at HATS, that type of thing. I think it's a little better than just doing it in class, plus it's a little different. Today we're going to talk about dependent and independent probability. And one thing I want to mention is when I'm doing these videos, you are still taking some sort of notes. All right, don't be surprised if I ask you to turn in the notes from a video. Dependent and independent probability. Independent. It's what happens in one event has no effect on the probability of another event. Two events that are completely independent. For instance, if you roll a die and then you spin a spinner, or if you flip a coin and then draw a card from a deck, one does not have anything to do with the other, completely independent. Let's do some examples. We have a die, we have a little spinning wheel. What's the probability of rolling a 4 and spinning blue? Well, first off, we can tell that this is completely independent. What happens on one has no effect on the other one. So we just look at our probabilities. What's the probability of rolling a 4? 1/6. There's 1 4 out of 6 total sides on the die. What's the probability of spinning a blue? Well, that looks pretty much like 1 out of 4. What do we do with these two fractions? We multiply. And when you multiply fractions, you do not need common denominators, but you do multiply straight across. 1 times 1 is 1. 6 times 4 is 24. On some problems in our packet, we can leave it as a fraction. In other problems, they want us to divide it into a decimal, and they want us to round it to 3 decimal places. The third decimal place in this answer is the 1. So we look at the 6. The 6 tells us to round up. So if they asked us for a decimal, 0.042 would be our final answer. Let's do another one. What's the probability of rolling a 5 or a 6 and not spinning a green? 5 or 6. Well, that's 2 of the 6 sides. And not spinning a green looks like 3 out of the 4 for the spinner. So now we, again, do not need common denominators. We can multiply straight across. 2 times 3 is 6. 6 times 4 is 24. We always reduce fractions. That is 1/4. If they asked us for a decimal, that's an easy decimal, 0.25. And again, we just look at each event by itself because one does not change the other. How about this? Dealing from a deck of cards with replacement. What's the probability you get dealt 10, Jack, Jack? So with replacement means after they give you your first card, you put it back in the deck, kind of like a magician or something would do. So we ask ourselves, this first card we want to get a 10. What's the probability we get a 10? Well, there are 4 10s in a deck of 52 cards. Now we put that 10 back in the deck, shuffle them back up, and what's the probability we get a jack? There are 4 jacks out of that deck, and there are still 52 cards because we keep putting the cards back. So now we have our jack for a second card, and we give it back to the dealer. He shuffles them back up, and we pick our third card. What's the probability of that being a jack? Well, that is also 4 out of 52. Before we multiply, it might be better to just reduce all of these fractions. That's 1 over 13, 1 over 13, 1 over 13. Multiply it out. And that's 1 out of 2,197. And that is too small of a decimal for us to even worry about. It's a whole bunch of zeros. So hopefully you get the idea there. How about this? Again, with replacement, what's the probability you get dealt an ace and a black card? So first card, we want an ace. There are 4 aces in a 52 card deck. We give that card back to the dealer, and then we say, okay, now we want a black card. And we know without reducing, it's 26 black cards out of a 52 card deck. And again, before we multiply, might as well reduce. That's 1 out of 13 and 1/2, which means 1 out of 26 times we can expect that we would get an ace and then a black card with replacement. This is the decimal. If you put the entire thing in your calculator, round to 3 decimal places, that's the 8. We look at the 4, and that tells us we do not need to round up, so 0.038 as a decimal. What's the probability of flipping a head and drawing a face card? So we're going to flip a coin. Everybody knows that flipping a head is 50-50 or 1 out of 2. What about a face card? Well, we said there's 12 face cards out of our 52 card deck. We might want to reduce that. To 3 out of 13. And now we can reduce. 3 out of 26. As a decimal, that's 0.1153846154. Third decimal place is the 5. We look at the 3, and that tells us just leave it, 0.115. These shouldn't be too confusing. In fact, you're probably already bored. So let's go to something else. Dependent variables, where what happens in one event does affect the other event. Let's show some examples. Here we have the letters Hatboro, Horsham. From the letters above, what's the probability you spell the word bat? And I forgot to type it in here, but it's without replacement. Without replacement. So once we pull a letter out of the bag, or however you want to think of it, we do not put it back. So let's see. If we want, first letter needs to be a bat, or a B, I'm sorry. There's 1 B out of Hatboro, Horsham, and that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 letters. All right, so now we get our B. So now we need to pick an A. And what's the probability that we would pick an A? And remember, we are not putting the B back. We're keeping it in our hand. Well, there are 2 A's out of 13 letters. Because, again, we did not put the B back. So we lucked out and we got an A, and it doesn't matter which one I cross out, I will cross out the first one. Now we need to pull that third letter, the T, and there is 1 T out of 12 letters. Multiply straight across, 1 times 2 times 1, and 14 times 13 times 12. 2,184. That reduces to 1 over 1,092. And if we do that on a calculator so we can get a decimal, again, really small zeros, so let's not mess with it. So this is without replacement. Our total number decreases because as we pull one out, there's one less. What if we wanted to spell the word robot from Hatboro Horsham? All right, well, we need an R. There's 2 R's out of 14. If right away you just wanted to reduce that, you can. 1 out of 7, but I'll just leave it 2 out of 14 for now. So we pick an R. Awesome. We need to get an O. There are 3 O's out of 13 letters. I pick an O. Now I need a B. There is 1 B out of the 12 remaining letters. But I picked that B. Sweet. Now it's time for the other O. I have 2 O's out of 11 letters. And now we need that final T. There's 1 T out of 10 letters. Oh, I'm sorry, I forgot to cross out our second O. So then there's 1 T out of those 10 letters. We can multiply straight across. We could do some reducing if we want. For instance, this 2 and that 12 can become a 6 and a 1. And this 2 and that 14 become a 7 and a 1. And this 3 and that 6 can become a 1 and a 2. Man, that makes it a lot easier because now I just get a bunch of 1s on top. And on the bottom, 7 times 13 times 2 times 11 times 10, 20,020. So there you have it. 1 in 20,000 chances about that you can spell robot from Hatboro Horsham. More without replacement. We want to draw some marbles and we want to draw red, green, blue. Chances of drawing a red, 10 out of 20. Or 1 out of 2. So I draw a red. Keep it in my hand. Now I want to draw a green. 3 out of 19. I'll keep it down here with our reduced column. I do draw that green. Now I try to draw a blue. 2 out of 18 or 1 out of 9. Let's multiply. First we could reduce. 3 and 9 become 1 and 3. 1 times 1 times 1 is 1. 19 times 2 times 3, 114. If it asked us to make it a decimal, 0.008779, so 0.009, because the 7 makes the 8 round up. So again, without replacement, our denominator, our bottom number, keeps getting smaller because there's fewer and fewer things for us to choose from.